Am I audible and visible, Shifra? Okay, thanks. Okay, so hello students. So today we are going to start second lecture of magnetic effect of current. We have discussed a basic concept of this chapter in the previous class, like what is magnetic field, how it is calculated, what are the sources of magnetic field. So we have discussed the small things in the previous lecture. Now we are going to start in detail study of this chapter. So first of all, we will just revise few of the things of the previous lecture and then we will start moving for the today's session. So just have a recall of the session in just 1 or 2 minutes. So let's recall. Okay. If I say what we have studied in the previous chapter, previous lecture, I will say, okay. So first thing that we have studied is what is magnetic field. If I summarize it in one line, then in this chapter, in this particular chapter, we are going to study that any current carrying wire or a moving charge creates magnetic field. So what we have learned is that moving charge or current creates magnetic field. That's one thing that we have learned in the previous session. How it is denoted by B, its unit is Tesla. Very simple. Now, next thing that we have learned is that how it is calculated. So that is Biot-Savart law is for that. And what it states, it states that magnetic field due to a very small element is mu naught over 4 pi vector IDL cross R divided by RQ. That's what we have learned in the previous class. Field is a vector quantity, so it must have a direction, and direction is calculated using the vector product IDL cross R. These are the basic things that we have learned. Now, another thing that we have learned is, if you can see that if there is a circular loop which carries some current I and has a radius R, then magnetic field at its center B is mu naught I over 2R. Remember these formulas, mu naught I over 2R. This is the field at the center of a loop. Now, on the same note, we have completed one more topic. What if the circle or the loop is not complete? Or what if the loop has number of turns, more number of turns? For example, if I say if it has n number of turns. Now, if it has n number of turns, it will be called as a coil. It will be called as a coil and it will look like something this one. Like this is one loop. Now there are more and more turns of this wire. So it will somehow look like that. All the turns will have almost the same radius like R and number of turns are N. Current carrying is I in each wire, each turn. So magnetic field in this case is mu naught. How many turns are there? N I over 2R. These are the things that we have completed in the previous session, I will say. Now, one more thing that I will ask here, or I have completed in the previous class, that was what if the loop is not complete, that it is just an arc. For arc, I will say like this is the arc. This is the center of the arc, radius of the arc, and this angle is theta. So for this situation, magnetic field was mu naught I over 2r is for the complete circle multiplied by theta by 360. These are the things that we have completed in the previous section. So that was the quick revision of all the things. If you were absent in the previous lecture, try note down these formulas and it will help you in this particular lecture. Okay. So on this behalf, I am moving further. So now it's time for your recall test. Let's revise the concepts. Okay. So what is the first question on your screen? Question is very interesting. What it says, it says a disk of radius r has a uniform charge of charge density sigma. So look at that. Let's suppose there is a disk. Let's suppose there is a disk which has a radius r. Now, no problem with that. And uniformly distributed charge. So charge is uniformly distributed on its surface like this, like this. And this charge density is given as sigma. Now, second question is it is rotated with some angular velocity omega. This is mentioned as omega, not w, it is omega. About an axis passing through its center and perpendicular to the plane of the disk. So there is an axis which is perpendicular to its plane like this. Now this disk is being rotated with some angular velocity omega. Find field at the center of the disk. First thing that I will clear you that this is the question asked in the mains examination. I am just not remembering the date and it's not important for you to remember the date, but it was asked in the JE exam. Quite simple question. You need to understand. Find the field at the center of the disk. You need to find the field. Now, what we know that whenever there is a current, a magnetic field is created. So first of all, you need to identify, you need to think like that, sir, where is the current? This is charge only. The disk is only charge. So where is the current? So I will say whenever this disk is rotated, the charge on the disk will also rotate in the same direction. So moving charge creates electric field. So there moving charge creates electric current. So there is current, and if there is current, there will be a magnetic field. So that's clear that there will be a magnetic field. Now we need to calculate this magnetic field. For this, let's just suppose, let's suppose there is a very small ring like this. If there is a ring like this, let's suppose its radius is x and thickness is dx. Now, why I am dividing this disk into a ring? If you can calculate the current in this ring, then you can calculate the field created by this small element, which is a ring. After that, you can integrate it. So my task is simple. First step, we are going to calculate the current in this small part, in this small elemental ring that we have considered. This ring will act as a loop. So we know the formula of magnetic field due to this loop. We will calculate that. We will write down this loop. So can you see that there are a lot of rings that can be formed of different areas, so we can integrate it. So let's try to find out the current. Okay. First of all, charge on the ring. You will say charge on the ring will be something very small, dq is equals to. From electrostatics, you know that sigma is the charge density and what is the area of the ring? You will say, sir, perimeter of the ring is 2 pi x. And what is the thickness? Dx. So this is the charge. Sigma into dA, sigma into area. Clear? Now, charge, we know that. Now, if you can see that, let's suppose this is a cross section of the ring. In one revolution, the charge will revolve complete round. So charge passing through this cross section in one revolution is this one. And current will be, if I write here current, I is equals to dq over dt. Now we know that charge is sigma 2 pi x dx. This is charge divided by time period. We have taken complete charge. This charge is rotated in one complete circle. So charge transferred divided by time period. Time period of revolution is 2 pi by omega. You can cancel out few things here. 2 pi and 2 pi will be cancelled. So I will be sigma omega x dx. This is current. This is the current in this. Now, magnetic field at the center due to this loop. You will say there will be a very small field dB is equals to, what is the formula? Just recall it, mu naught I divided by 2 and radius. Radius of the loop is x. So you can write it again using different color. dV is equals to mu naught I, you just put the value sigma omega x dx divided by 2x. X and x can be cancelled again. So dV is what? Mu naught sigma omega by 2 d. Clear? Now this is the magnetic field. Now what is the complete magnetic field? You will say complete magnetic field will be integration of this one, that is mu naught sigma omega by 2 ds. From where to where? 0 to r. 0 is the center, r is the extreme point, radius. So if you integrate it, it will become, you can take out the constants, that is mu naught sigma omega by 2. Integration of dx is x, limit is r, that is. So B is equals to mu naught sigma omega r by 2. This is the magnetic field at the center of the disk. Are you getting my point? How we can calculate the magnetic field? Is this point clear to you? Okay, so this is the basic question that you should know how to apply the basic. It's not like every time you will get a loop and you need to find the magnetic field due to the loop only. You have to implement these knowledge. You have to implement these things. I think it is clear. Moving further. This is again a very simple question based on the loop, concept of loop. You need to solve it by your own. This is your homework. So try to take the screenshot or write down the question. You can pause the video, whatever you want to do. It is your homework. Answer is also mentioned here. There is another question. I'm solving this question here. You need to read the question well, actually. What it says, a current loop consists of two identical semicircular parts. Okay, one thing in my mind clear, two semicircular parts, each of radius r. One lying in the xy plane and other in the xz plane. So first of all, you need to draw xy and z axis. Okay. I'm just drawing. Let's suppose this is our x axis, y axis, and this is our something z axis. Clear? The xy plane, like this, you can say, I think it looks like a semicircular part. You can consider it. If not, you can consider. This is a semicircular part of radius are placed in the xy plane. This is x, this is y, and this is z. Very good. Now another part in the xz plane, I'm trying to draw it. Is it clear that this is horizontal and first part is vertical? This is xy plane. This is xz plane. It is horizontal plane like this. You can see my hand. This is this one, second one, and first one is like this. So overall picture will be something like that. These are the two semicircular parts of the loop. I think it is clear, visible. Okay, yeah. Now both have same radius. This is the common center. So they are asking the resultant magnetic field due to the two semicircular parts at their common center. Okay. And they have a current I, it is mentioned there. Now, first of all, let's consider a current I. Let's suppose this is the current I. So this will be current I. Like this is the current. Okay. Let's suppose this is part one, this is part two. What we will do, we will calculate the magnetic field due to each part one and part two, and will add those two magnetic fields according to the vector rules. And that will be our answer. Very simple question. Okay. So let's try to solve it out. First of all, if I say both the parts have same radius and same current, and these both the are the semicircles, so field will be identical. Field will be identical. So I am mentioning that B1 should be equals to B2, and it should be. I am talking just about magnitude because there is no vector sign I am mentioning here. So what will be the magnitude? You know that for a circular arc, mu naught I over 2R is the magnetic field. This is for the complete loop, and you are considering a semicircle. So you remember the formula mu naught I over 2R theta by 360. And if you consider a semicircular loop like this one, what will be the value of theta? You will say, sir, 180 degree. So that is 180 by 360. So what will be the magnetic field? B1 is to equals to B2 is equals to, this is 2 mu naught I over 4R. Now remember, these things you can solve in your mind and you can directly write it as mu naught I over 4R without writing these two steps. Okay. This is the magnetic field of one of each loop, I will say, or each part of the loop. Now, what will be the direction? What will be the direction? If you talk about B1, part 1, the if you I curl the fingers of my right hand in the direction of current, then it will be into the plane. Into the plane means I am writing the direction cross. If I talk about B2, the current is in the horizontal plane and I am curling my fingers, then it is in the downward direction. The direction of magnetic field is downward. What will be the angle between these two magnetic field? You will say one is inward, one is downward. The angle will be 90 degree. Now remember this one punchline, and everyone should remember. I am not going to solve it out. You just need to remember this punchline. What is the punchline? Whenever two equal vectors are to each other, remember, whenever two equal vectors are perpendicular to each other, the net resultant of these two vectors is root 2 times is root 2 times the original vector. Original vector is either v1 or v2 because both are equal. So I am just writing the answer in the same way. So net field will be root 2 times v1 is what? Mu naught I over 4r. You can cancel these things and that will be, you can say that b net is equals to mu naught I over 2 root 2r. This is your correct answer, which is option number A, which is option number A. So correct answer is option A, right? Moving further. Now we are moving towards the next concept. This is field due to a straight wire. This is the most important concept, I will say. Most important. Clear? So let's suppose this is a straight wire. Let's suppose this is a straight wire and it has some current. Let's suppose it has a current I and you need to find the magnetic field due to this wire at this point. Let's suppose this point is P. Clear? Till now everything is clear. Moving further. Now, first of all, the perpendicular distance of the point, mark my word, the perpendicular distance of the point P with the wire is A. Let's suppose. Till now everything is clear. Now, one more thing I will say, the ends of the wire, let's suppose this is end A, this is end B. The end of the wire, the end A of the wire makes an angle, I will say, let's suppose theta 1 with this perpendicular. I am again saying with this perpendicular makes an angle theta 1 in the, you can say, in the anti-clockwise direction. What is the direction? Anti-clockwise. And the end B makes an angle theta 2 in the clockwise direction. So I will write it as clockwise. This is anti-clockwise. Okay. So what is the magnetic field at point P? If I calculate, I am not going to drive the relation. If I write this magnetic field, you need to write it on your pen. What it will be? B is equals to mu naught over 4 pi I divided by A. Remember each and every term. What is A? A is not the distance. A is the perpendicular distance of the point from the wire. I will explain you. Now, in the bracket, sine theta and with the limit minus theta 1 to theta. This is our sign convention, taking anti-clockwise as negative and clockwise as positive angle. Now, this is the basic standard relation. Everybody knows that you need to put the limits on this. Remember this one. Remember it. Or you can put it in a golden box. Now, if I simplify this after putting the limits, it will become B is equals to mu naught over 4 pi I by A. If I put the limit sine theta to minus sine. Now this minus sine minus sine theta. So this minus and minus can be cancelled out. I think this simple mathematics, you know. So ultimate result is on your screen. This is the magnetic field due to not over 4 I by A sine theta 2 plus sine theta 1. This is the final result and this is the standard result. My recommendation, you should remember both. Actually, you should remember both. Is this thing clear? Now, when you can use this result directly, whenever the point lies, the point P, this point P lies, or you can say the ends of the wire are on either side of the point P. Like this is point P, point A is below it, and point B is above it. In that situation, or you can say point P is somewhere in between the wire, then you can use this relation directly without any hesitation. You can directly use it. But if something unusual happens, like both the points A and B are on one side of the wire, on one side of the point, then you can't use this relation. You have to go to the basics. That basic is this one. First of all, write down the formula before moving further. Write it on your notebook so that we can use it whenever needed. Clear. Moving further. Now there are some special cases. I will look at that first. Now, first is if wire is of infinite length, or you can say long wire. Long, whenever I say long wire, it means of infinite length. That is very long wire. Actually, infinite is nothing, but let's suppose. So for this situation, let's consider there is a wire. There is a wire. This wire is of infinite length, like this one. Mm, goes beyond, 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 and this one is also going beyond, 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 like this. And this is some point P. Clear? Now, know that this is the perpendicular. This distance is A. You can see that both the ends A and B of the wire are on two different sides of the point P. So we can directly use the relation B is equals to mu naught over 4 pi I by A sine theta 1 plus sine theta 2. We can directly use this relation. Now, if we can directly use this relation, now what you should do, put the values of theta 1 and theta 2. We have already used the sign in the integration limit, so you don't need to put the sign now, whether it is anti-clockwise or clockwise. Now you can see that if I initially the wire was something like that, this angle was theta 1. If I increase, like if wire, the length of wire is increased, then this angle theta 1 will increase. Can you see that? Theta 1 is increasing. But if it is increased infinite times, then this angle theta 1 is increasing and increasing and continuously increasing up to a maximum value of 90 degree. So for infinite wire, the maximum angle that a end can form is 90 degree. So theta 1 and theta 2 both are 90 degree. If you put theta 1, theta 2 90, sine 90 plus sine 90, that will become 1 plus 1, that is 2. So what is the ultimate result? Mu naught over 4 pi 2I by A. The calculation of current direction of field is same as told in the previous lecture. So this is the standard result you should remember for long or infinite wire. Always remember. Next thing, moving further. Next special case that can be formed here. Second special case for semi-infinite wire. If I talk about semi-infinite wire, you can see that, let's suppose this is a semi-infinite wire. What is the meaning of semi-infinite? This is end A of whatever, and this end is up to infinity. So end B is up to infinity, and point P is somewhere here. So this is our perpendicular distance A. Clear? Again, if I write magnetic field in this case, B is equals to mu naught over 4 pi I by A. This is clear. Sine theta 1 plus theta 2. This angle is 90 degree. So one angle is 90. And another angle, this point A makes zero angle plus sine 0. So final result is mu naught over 4 pi I by A. This is the final result for semi-infinite wire. Now I think something is getting cleared in your mind. After getting these two special cases, I have one or two more special cases for you. You need to understand those things as well for the smooth understanding. Now, again, if I say third special case, always remember these things. For collinear points, for collinear points, what should I mean or what does it mean that collinear points? Have a look at that. For example, this is a wire AB of any length, semi-infinite, infinite, finite, whatever may be the length, but this is a straight wire. And if this is a straight wire and any point on this line, like this, any point on this line, like this point P, this point, any point, these are the collinear points. Similarly, these are the points. This is the current carrying wire which has current I. So for these collinear points, magnetic field is zero. This is another punchline. That means for collinear points, magnetic field is zero. Clear? Now, this is the condition for straight wire only. Now, someone may confuse you with a simple question like someone may ask you, this is a circular loop or semicircle, and this point is collinear like of this part. Is the magnetic field zero at this point? Someone may remember instantly that for collinear points, field is zero. Yes, so for this part, magnetic field is zero. Remaining part, there will be magnetic field. So you cannot say that field is zero. So B is another case. Okay, give me just 1 minute. I will check. Yes, Shipra, is it audible now? Okay, thanks, thanks. Okay. So what I was discussing that if point P is outside the wire, outside the wire, this is very important thing to understand for both of for all of you. In fact, I will say. So let's take a simple example. Let's suppose this is try to understand all the things here. Let's suppose this is the wire AB. It may be of any length. That's not the important thing here. And let's suppose point P is somewhere here. This is point P. So this point P is outside. Now, first thing is that, first of all, you need to find the perpendicular on the wire, because this wire is only AB part is the wire. If you need to draw the perpendicular, you must need to extend the wire. So this white line is not the part of the wire. Current is only in this part from A to B. And you have extended this part to draw the perpendicular, and now you have drawn the perpendicular. So this perpendicular distance is known as A. I think this point is clear that I was discussing previously. So this point is clear. What is A? A is the perpendicular distance, how you can draw the perpendicular distance. Now, next point is, what are the angles? So this and A made an angle, you can say theta 1 with the perpendicular. And this theta 1 is again clockwise. And this and B, let's suppose, makes an angle. This line is just not a straight line. You can understand that thing. This is theta 2. So now here you can say both the angles are clockwise. Both the angles are in clockwise direction. So how you can write the magnetic field? Just remember the standard result, that is B is equals to mu naught over 4 pi. I hope you remember the standard result. You can speak in your mind, or you can write it by yourself without watching my part. That is I by A is the perpendicular distance sine theta with the limits theta 1 to theta 2. There I have used minus theta 1 because angle was anti-clockwise. Here both the angles are clockwise, so that is theta 1 to theta 2. Now if you put the limits, it will become mu naught over 4 pi I by A sine theta 2 minus sine theta 1. Is it clear? And the direction, you can directly use your right hand thumb rule for this wire at point P. If I recall things, just put the right hand, just take your right hand and put the fingers in the direction of current, the nails of your fingers in the direction of current, and that is the direction in the upward direction. Now turn your palm in the direction of the point, which is at the right, and curl your fingers, thumb will be into the plane. So field will be clear. Step related to this is clear. Okay. Okay, so there is a question on your screen. Just have a look. It's carrying same current I as shown in the figure. Okay, find magnetic field at the midpoint of the line joining the two wires. Let's suppose this midpoint is nothing but P. What you will do, I'm just telling you, I'm not going to solve it out. I'm waiting for your answers if you can, and you need to put it in the comment. So if you can see that this distance is A by 2 and this distance is also A by 2. Why? Because this is the midpoint. Now you know the distance. Can you see that this is the perpendicular distance? Yes, it is perpendicular distance. Now, are these wire are long? Let's suppose this is wire 1, this is wire 2. Yes, sir. If these are the two wires carrying same current, perpendicular distance is same, can you say that field will also be same? So I will say B1 is equals to B2. Magnitude of fields will be same. You know, particular question that you can say that is u not over 4 pi. Directions. If I say the directions of V1, just tell me the direction of V1. Do it yourself. Use your right hand and find the direction. And if you find the direction, it will be into the plane. And if you find the direction of B2, just try to find it out. Put your right hand in the direction of current and palm in the direction of point. So I am putting this, curling my fingers, thumb is outward. So thumb will be outward. So this will be denoted by dot. Okay. One more thing I will say, whenever you are watching this video, try to find out the direction by your own, because without that, without this concept of direction, you can't solve a simplest question, I will say, you just can't solve that. So try to do, don't hesitate in front of your class, in front of your teacher, just try, take your right hand, do the gestures, and you will be comfortable with it in the later stage. Now, both these vectors are opposite to each other, their magnitude is same. If magnitude is same, direction is opposite, so net field will be what? Will be what? Zero. Is it clear now? Is there any doubt? Okay, I think this is clear. Moving further for the next question. This is the question. Again, a very simple question. You can do it in your homework. I'm giving you in this question in your homework. I am moving further for the next question, which is very important. Now, have a look at that. Okay. Find magnetic field at point P. First of all, you need to find the wire. So this is the wire. Let's suppose this is point A, B, C, and D. So A, B, C, D is the wire. A, B, C, D is the wire. Can you break down the wire in some parts? Like this is part 1, this is part 2, and this is part 3. Clear? Can you break down the wire in these 3 parts? Okay. Now just imagine what you should do. Net field is equals to magnetic field of part 1 plus magnetic field of part 2 plus magnetic field of part 3. You need to calculate the magnetic field of each part and then add it according to the vector addition. As simple as that, principle of superposition that you have learned in electrostats. Now, can anyone notice that part 1, if you consider this is AB part, and this A point P is, can you see that collinear with part AB? According to the third spatial case, the magnetic field of part 1 is 0. Clear? Is it clear? You can see that. Now, if you consider the part CD, this point P is again collinear with the part CD. So magnetic field of part 3 is again 0. So now you have to solve for B2 only. Your aim is just to calculate B2. Now you can notice that point P is on one side of wire BC. Only one side. All those 2 points B and C or the complete wire is below the point P. That means the standard formula sin theta 1 plus theta 2 is not applicable here. You have to write the standard form. So if I say B2 is equals to mu naught over 4 pi I divided by, the distance is not given. I am just giving it to you now because it is the part of the question. This distance is given as A. Can you see that this distance A is the perpendicular distance because wire is BC? You need to extend it to draw the perpendicular, and this is A. So that is I by A sine theta with some limits. Now you need to find the angles. The angles are given as 30° with the perpendicular and 60° with the perpendicular. Both these angles are in clockwise direction. Can you see that? That means both should be positive. So I am putting the limits in the positive terms, that is 30 to 60. Now you can solve it out. Mu naught upon 4 pi I divided by 8 sine 60 minus sine 30. Can you solve it very quickly? That is mu naught divided by 4 pi I by 8. Sine 60 is root 3 by 2 minus 1 by 2. So 2 will be the LCM, that is root 3 minus 1. So that will be your answer. That will be your answer. You can again simplify it whatever you want. This can be written as 8 pi. So that's your part. This is B2. Now I am not going to write B as equals to B2 because B1 and B3 all are 0. So net field is equals to B2. So this is your answer, final answer. Clear? I hope it is clear. Moving further for the next question. There is again another question. Find magnetic field at P. After learning previous question, can you solve this now? Okay. First of all, have a look at the question. In how many parts you can break this wire? We can break it in two parts. Like this is part 1, this is part 2. Clear? And you need to find the field at P. And again, you can write it as net field at B is equals to field due to B1, part 1, and field due to part 2. Addition of these two fields. Very simple. Now, if I talk again, point P is collinear to part 2. You can see that. Physics is very interesting. Now you can clearly see that B2 is 0. Clear? Because point P is collinear. Now what is remaining? B1. So we will calculate B1 here. For B1, first thing that you should know is the perpendicular distance. That's what you should know. So you need to draw the perpendicular on the wire on the part 1. Let's suppose this is A, B, and C. Up to infinite they are going. So for part AB, you cannot draw the perpendicular this way. For that, you need to extend the wire AB. So I am just extending the wire AB. Let's suppose this is the extension of wire AB. This is not the part. Let's suppose I have drawn a perpendicular. So this is the perpendicular. Clear? So this is the perpendicular distance. So now in this question, this is not A. You need to calculate this distance. According to the geometry, this angle is going to be 45 degrees. Are you getting my points, or is it going just beyond your level? If you are saying it is beyond my level, then you have to increase your level. You just have to increase your level and try to understand the things here. Okay, listen to me again. Now this distance you need to calculate. Can you see the triangle? This right angle triangle. Can you see this? In this right angle triangle, this is the what it is. This is perpendicular. So that will be A sine 45. And sine 45 is root 2, that is A by root 2. Clear? So this perpendicular distance is A by root 2. This is what perpendicular distance. I think this is clear. Now, what are the angles? What are the angles? Can you see that? This is the end A and this is the end B. And B, how much angle it makes? If I change the color of the pen, if I try to recall things to you, what you have learned, this is wire AB. You have learned in the previous topics. This is point P. This is the perpendicular here. So the end A makes an angle theta 1 and B makes an angle theta 2. So can you identify the angles now? The end A and end B, how much angle they form with the perpendicular? So this is the perpendicular. So and B makes an angle 45 and A makes an angle 90 degree. And both these angles are clockwise. Both these angles are clockwise. I'm just staying there for just 2 seconds so that you can figure it out that how I have calculated the angle. So now you just need to put the limits. B is equals to or B2 is equals to mu naught over 4 pi I by A sine theta with the limits. What are the limits? 45 to 90 because all the angles are in the clockwise direction. Now, if the angles are such that you can put the limits and solve it. So B2 or you can say B is equals to B2 is equals to mu naught over 4 pi I. And what is A? A is A by root. So you can transfer it minus mu naught over 4 pi I root 2 by A. Sine 90 is 1 minus sine 40y is 1 by root. Can I summarize the answer now? Can I write down the final answer? Yes, sir. That is B is equals to mu naught over 4 pi. Can you see that if you take the LCM, it will become root 2 minus 1 by root 2. And this root 2 and this root 2 can be cancelled. So that is I by A root 2 minus 1. This is your final answer. Is it clear to everyone? On this note, I am giving you some homework. First of all, I hope the concept is clear. All four special cases, the straight wire case, everything is clear. Now there are some previous year questions, or you can say practice questions. These are mostly PYQs. I'm staying for each question for something 30 seconds so that or 10 seconds so that you can pause or question more. There are how many parts? One, two. Can you see the four parts? To find the field at point O. Linear with two parts. You can see that for part number two. So that's why I can write it as B2 is equals to B4 is equals to 0. Can you directly use this? And 3 and 1 are are some circular arcs. So you can calculate the angles as well. You can calculate the field for circular arcs. So there is one more question. Four questions are there. After that, we will start new concept. Till then, enjoy, learn, keep learning, keep revising, and it's goodbye from my side.